Look up at the night sky. It's filled with stars, planets, and galaxies, each one a tiny part of a much larger cosmic tapestry. Have you ever wondered where it all came from? What sparked the creation of such a vast and intricate universe? How did this vast and complex universe begin? What forces were at play in the birth of everything we know? For centuries, humans have pondered these fundamental questions, gazing at the stars and seeking answers. Seeking to unravel the mysteries of our cosmic origins, scientists have dedicated their lives to understanding the universe. The prevailing scientific explanation for the birth of our universe is the Big Bang Theory, a concept that has revolutionized our understanding of the cosmos. It's a story of incredible density, unimaginable heat, and the birth of everything we see around us. The Big Bang Theory suggests that the universe began from a state of extreme density and temperature, a singular event that set everything into motion. The Big Bang Theory suggests that the universe began from a state of extreme density and temperature, a singular event that set everything into motion. Imagine everything in the universe squeezed into a tiny point, smaller than an atom. This point, called a singularity, held all the potential for the universe we know today. This point, called a singularity, contained all the matter and energy that would eventually become stars, galaxies, planets, and even us. Contained all the matter and energy that would eventually become stars, galaxies, planets, and even us. Then, something extraordinary happened. This singularity didn't just sit there. It began to expand. This singularity didn't just sit there. It began to expand, setting off a chain reaction that would lead to the universe as we know it. This wasn't an explosion in the traditional sense, like dynamite going off. Instead, it was the expansion of space itself, a process that continues to this day. Instead, it was the expansion of space itself. Imagine a tiny balloon with dots drawn on it. Imagine a tiny balloon with dots drawn on it. As you inflate the balloon, the dots move farther apart, just like galaxies in our expanding universe. As you inflate the balloon, the dots move farther apart. Similarly, as space expanded, the early universe stretched and cooled. Similarly, as space expanded, the early universe stretched and cooled, allowing for the formation of atoms, stars, and galaxies, setting the stage for the formation of the structures we observe today. From the smallest particles to the largest galaxies, everything began with this incredible expansion. The Big Bang Theory wasn't born overnight. It was the culmination of years of research, debate, and groundbreaking discoveries. It emerged from the brilliant minds of scientists who dared to challenge conventional thinking, pushing the boundaries of what was known and accepted. One such mind was GeorgesLemaître, a Belgian priest and physicist. Lemaitre was not just a man of faith, but also a man of science, bridging two worlds that often seemed at odds. In 1927, Lemaitre proposed the idea of an expanding universe, suggesting that it originated from a single, incredibly dense point, which he called the primeval atom. Lemaitre's idea was revolutionary, challenging the prevailing notion of a static universe. At the time, most scientists believed in a static, unchanging universe. The idea that the universe could be expanding was almost unthinkable. But Lemaitre's calculations, based on Einstein's theory of general relativity, pointed towards a universe in motion, a universe that had a beginning. His work suggested that the cosmos was not eternal and unchanging, but dynamic and evolving. Around the same time, an American astronomer named EdwinHubble was making groundbreaking observations that would further support Lemaitre's theory. Using the powerful Hooker telescope in California, Hubble observed distant galaxies. His observations were meticulous and detailed, providing new insights into the nature of the universe. He noticed something peculiar. The light from these galaxies was stretched, shifting towards the red end of the spectrum. This redshift was a crucial clue. This phenomenon, now known as redshift, provided the first observational evidence that the universe was indeed expanding. It was a monumental discovery. Hubble's observations were like finding a cosmic speedometer, measuring the rate at which galaxies were moving away from us. Just as the sound of a siren drops in pitch as it moves away from us, the Doppler effect, the light from distant galaxies stretches, shifting towards the red end of the spectrum as they move away from us. This analogy helped make the concept more understandable. The farther the galaxy, the greater the redshift, and the faster it's moving away. This relationship was key to understanding the scale and dynamics of the universe. This discovery revolutionized our understanding of the universe, confirming Lemaitre's predictions and paving the way for the Big Bang Theory. It marked the beginning of a new era in cosmology, where the universe was seen as a dynamic, ever-expanding entity. The redshift of distant galaxies wasn't the only evidence supporting the Big Bang Theory. In 1964, two physicists, Arno Penzias and Robert Wilson, stumbled upon another crucial piece of the cosmic puzzle, the cosmic microwave background radiation, or CMB. While working on a new antenna at Bell Telephone Laboratories, Penzias and Wilson detected a faint, persistent hiss in their data. This hiss, they soon realized, was coming from every direction in the sky. It was a faint afterglow of the Big Bang, the cooled remnants of the intense heat and energy present in the early universe. Imagine a bonfire. Long after the fire has died down, you can still feel the heat radiating from the embers. The CMB is like the faint warmth of the early universe, a cosmic echo of the Big Bang that has been traveling through space for billions of years. The discovery of the CMB was a major triumph for the Big Bang theory. It provided tangible evidence of the universe's hot, dense beginnings and solidified the theory's place as the leading explanation for the origin of our universe. Section 4. From singularity to the cosmos, the universe unfolds. The Big Bang theory paints a picture of a universe in constant evolution, transforming from an unimaginably hot, dense state to the vast cosmos we observe today. This theory, supported by a wealth of observational evidence, suggests that the universe has been expanding and cooling for billions of years. In the first fraction of a second after the Big Bang, the universe was an inferno of energy, a seething cauldron of particles and forces. This initial moment was incredibly chaotic, with temperatures and densities so extreme that the fundamental forces of nature were unified. As space expanded and cooled, this energy began to condense into matter, forming the building blocks of atoms, protons, neutrons, and electrons. These particles are the essential components that would later combine to form the elements we know today. For hundreds of thousands of years, the universe was a hot, opaque soup of these particles. During this period, the universe was so dense that light couldn't travel far without being scattered. Light couldn't travel freely. It was constantly scattered by the dense plasma. This scattering kept the universe in a state of darkness, preventing any light from escaping. But as the universe continued to expand and cool, a crucial transition occurred. Atoms formed. This process, known as recombination, allowed electrons to bind with protons and neutrons, creating neutral atoms. With electrons now bound to atomic nuclei, the universe became transparent. This transparency marked a significant milestone, as it allowed light to travel freely through space for the first time. Light could finally travel freely, and the universe, once a cosmic fog, became visible. This transformation from an opaque to a transparent universe is a key event in cosmic history. This era, roughly 380,000 years after the Big Bang, is what we see when we observe the cosmic microwave background radiation. This faint glow provides a snapshot of the universe at that early time. Over millions of years, gravity began to sculpt the universe. The force of gravity pulled matter together, creating the large-scale structures we see today. Tiny fluctuations in the density of matter, amplified by gravity, caused matter to clump together. These small variations were the seeds of future cosmic structures. These clumps grew larger and denser, eventually collapsing under their own gravity to form the first stars and galaxies. This process of star and galaxy formation continues to shape the universe, creating the diverse and dynamic cosmos we observe today. Section 5. Modern Eyes on the Cosmos. Observations and Simulations. The Big Bang theory isn't just a story from the past. It's a framework for understanding the ongoing evolution of our universe. Modern telescopes like the Hubble Space Telescope and the James Webb Space Telescope allow us to peer deep into space and time, observing galaxies at different stages of their evolution. These observations provide valuable data that help us refine our understanding of the Big Bang and the processes that govern the universe. By studying distant galaxies, we can piece together a timeline of the universe's history, from its early chaotic beginnings to the formation of the large-scale structures we see today. In addition to observations, scientists use powerful computer simulations to model the evolution of the universe. These simulations, based on the laws of physics and our understanding of the Big Bang, allow us to recreate the conditions of the early universe and study how galaxies and other cosmic structures formed. By comparing these simulations to actual observations, we can test the accuracy of our models and gain a deeper understanding of the processes that have shaped the universe over billions of years. Section 6. Challenging the Big Bang Alternative Theories and Cosmic Puzzles. While the Big Bang theory is the most widely accepted explanation for the origin of our universe, it's not without its challenges and mysteries. Scientists are constantly searching for answers to questions that the Big Bang doesn't fully address. One such question is the nature of dark matter and dark energy. These mysterious entities, which we can't directly observe, are thought to make up the vast majority of the universe's mass and energy. Understanding their properties is crucial for fully explaining the universe's evolution. Another challenge is the horizon problem. The CMB, which comes from all directions in the sky, is remarkably uniform in temperature. This suggests that different regions of the early universe, even those vastly separated, were somehow in thermal equilibrium. But how could this be possible if information can't travel faster than light? These challenges have led some scientists to propose alternative theories to the Big Bang, such as the steady-state theory, which suggests that the universe has always existed and has no beginning or end. Others have proposed the existence of a multiverse, where our universe is just one of many. Section 7. The ever-evolving understanding of our universe. The Big Bang Theory is a testament to the power of human curiosity and our quest to understand the universe we inhabit. It's a story that's still being written, with each new observation and discovery adding a new chapter to our cosmic narrative. While the Big Bang Theory provides a compelling explanation for the origin and evolution of our universe, it's essential to remember that science is an ongoing process of discovery. There's still much we don't know about the universe, from the nature of dark matter and dark energy to the possibility of other universes. As we continue to explore the cosmos with increasingly sophisticated tools and technologies, we can expect to uncover even more surprises and mysteries. The Big Bang Theory may be our best current explanation for the universe's origins, but it's likely just the beginning of our cosmic journey. The universe is full of wonders waiting to be discovered, and it's up to us to keep exploring, questioning, and pushing the boundaries of our understanding. So keep looking up at the night sky and asking those big questions, for they are the driving force behind our quest to unravel the mysteries of the cosmos.